Hello, folks. It's 8 a.m. PST, so we might as well get started right at the beginning of the hour. It's been about 3 weeks, so thanks again for your patience while pulling this book club together. I had a pretty good trip to Wisconsin, actually. Got to see my friends get married, so that's where I was last weekend. But now just straight back to it. So for those who've been following along, we're now covering large language models, or let's say generative AI in general, but it's a really wide and expensive topic. So the previous couple sessions, we had covered model basics and we'd covered Flax. Now we're going to start diving into the start of language models themselves. So not just neural networks, not just neural networks in general, and the neural network architectures, but language models. And today we're going to cover a couple of topics. We're going to cover language model intuition, what I'm going to coin small language models, which really they were called language models up until maybe 3 or 4 years ago, and then now what has been coined as large language models. And it's going to be mostly going to be sort of theory, I shouldn't say theory, but mostly at a high level, because I think when in this book club, a lot of us think about building our own, like let's say ChatGPT or something like that, and it's not just the language model that does that, but a whole bunch of other things that come together to make that possible. So we're going to cover what I'm going to say is the engine of these large language models, which is the transform itself, and then I'll talk about in the next sessions how we'll get to the rest of it. But before I get too ahead of myself, always curious who is here today. Usually we have a couple of typical suspects that I've now updated my priors to say are always here. So let me know if you're here. Let me know which topics you're particularly interested about. Today will be more of a free-form session rather than a very structured and specific set of topics and notebooks that we have to go through. So as I always say, I hope we take less than an hour. I think today we're actually going to take less than an hour, but let's see. Always have Chad. I appreciate that. Good morning, Chad. Hope you're still in Portland and doing well. And then we'll see who else who drops in. All right, we got Julio and Chad. So it's a party. So let me pull up. All right, we're all set here. So the first thing is, as I was going through this and I was trying to create this book club, as you folks know, the three that are here, we've tried to follow actual books, and we did with the causal inference mixtape. So for folks who've been on this book club a bunch, you've seen this a ton. Oh. But we really enjoyed the causal inference mixtape because it was free and online and accessible. It had a nice story narrative with graphics, and it included code and math together. So this was fantastic, and it did a really good job going all the way from the text to the actual application. I have not been able to find anything for these large language models because it is such a new topic. With large language models, we have a bunch of theory and papers that are coming out every day. Now we have a bunch of tweets and blog posts, and then we have a bunch of code examples, and they're all in different places. So as part of this book club, what I'm going to do, or I already have started doing, is I'm just going to start writing what I'm calling a guide. And this guide isn't meant to be a comprehensive reference, like a single reference. But what it's going to have is it's going to have lots of different references to all sorts of things you can go to. So let's say if you were going back to the basics of neural networks and somebody wanted to try out and understand neural networks, I'm linking the things or the best snippets and code and resources that I found on the internet. So in this case, this TensorFlow Playground does a really good job of helping you understand how neural networks work. If we have, let's say, 2 features and only 1 neuron, the model can't fit this data particularly well. But let's say we add a bunch of neurons and make this more complex. Well, suddenly this model does a really good job. And so this TensorFlow Playground is just a really great resource to go in and just get the intuition of a neural net. And it's not in a book, and it was just something that I'd found a couple years ago, so I'm linking it here. Oh, I lost it. In that same manner, if you're looking to then get an exhaustive understanding of neural networks, I'm linking what I think is the best single course on neural networks, which is this classic from CS231. CS231 from Stanford, and it has tons of material, like lots and lots and lots and lots and lots of material. Like it goes into all the details. So what it is, what this guidebook is going to be is like the name implies. It's a guide to various places, and what I found to be really nice references. Of course, I have to represent myself and put in my own book club, but that's the one we covered before. That's our last session. Neural network architectures, why we have them, some analogies, and then some explanations and blog posts from when to use different architectures like multi-layer perceptrons, convolutional neural networks, recurrent neural networks. That's what this resource is. It is still, I'm still actually now writing it in conjunction with the book club, so a bit of a lot, but we're going to be using this going forward. So we've already done GenAI Foundation, so I'll come back and finish this out later. But what we're getting into is language models themselves. There's a lot of stuff to go over in language models. So I've put it here at the bottom, but when you talk about language models, it's not just the transformer that goes into it. There's tokenization, there's things called embeddings, there's a bunch of training strategies like masking and packing. There's a bunch of tuning strategies like supervised fine-tuning, reinforcement learning with human feedback, reward models, which are models trained to train other models. There's a bunch of things going on with serving these models, so context windows and things like that. That's changing all the time. Model distillation and so on and so forth. I have not found, well, we're not going to cover this all today because it's too much. And again, like I've pointed out, I haven't found a single great resource to cover all of this. And the last part that makes this hard is it's changing every day. So when we started this book club, there wasn't a 10,000 token ChatGPT model available. And I don't actually think there was a 10,000 token model available from anybody. But now, 2 months later, there is. And there's a lot of research going on how the original transformer can be scaled to handle these crazy context windows. Now, I'm probably saying a lot of terms. Actually, I am saying a lot of terms that I haven't covered yet. The purpose of this study club is for you folks to have a reference. Well, for you folks to hear these words for the first time, at least from me, and then have a reference to cover it all. So for today, we're going to do 3 things. I'm going to talk about at a high level how we got here. That's this one. Small language model intuition, and I'll show you some resources below where you can read and watch some nice videos to get some more intuition, and then large language models and a transformers overview. Again, in this particular study club, for today, what's going to happen is I'm going to cover the intuition at a high level, and I'm going to point you to a lot of resources. So I'll try and answer questions here and there. I'm not an expert on every single topic, but I'll at least try and get you to expert resources on each one of the topics. So with that, I'm going to say if you have any questions or anything you want to talk about in particular, again, leave it in the chat because it takes a little while for the stream to get you. But while you're doing that, I'm going to get to how we got here and then small language intuition. So I will point out in addition to writing this, I've been trying to figure out how to structure it, and unfortunately what that's meant is I haven't had a lot of time to typo fix and read everything and fix it up myself. but let me talk about how we got here. The simplest answer, which is sort of unsatisfying, is that language is important for humans. It's how we communicate. It's how we're talking right now. So it's always been interesting to folks to break down and understand languages. And in recent years, modeling that mathematically. So just like when we were in the causal inference book club and we wanted to mathematically model causal inference, there was a set of strategies and assumptions in mathematics that we used to do that. For a brief period in the state space model book club, we wanted to model various things like time series or random events. And there was a structure and way of doing that. But with language, things are a little bit tricky because language doesn't follow strict mathematical rules, and it's not sort of self-contained, right? Language is this ever-evolving thing that isn't defined by mathematics. It's what we as humans make up. But it's been something that's been studied for a really long time. So sometimes I feel like there's a perception that language models have just started out now, maybe the last 10, 20 years, but people have been studying it for quite a long time, and we're going to go back as far as 1948. So not new stuff, way back to the middle of the 19th century, to Claude Shannon's work. Now, in addition to folks thinking that language models are new being a misconception, I think another thing that's been happening recently is that it feels like people think it's you just have an input string. Like, let's say, hello, my name is. It just goes straight to a transformer, and then you get an output. But the reality is much more complex, as I alluded to earlier. There's a lot of steps that go in between the input string and the output, and a lot of shaping that occurs in multiple steps to produce something like ChatGPT. So things like I said, tokenization, embedding, training methods, but even these days, factors like publicly available compute capacity are all constraints that get in the way of producing these larger language models. So again, in this book club, we're going to cover all of that, hopefully, well, ideally. We'll talk about not only the mathematical underpinnings, but all of the factors that are going to shape these models. Some of them mathematical, some of them process, and some of them compute. So a lot of these concepts are abstract as well. And so I'm going to use the same bike analogy that we used a couple weeks ago. And so if you think about a bicycle, just real quick, it seems obvious now that we have bicycles and they're everywhere and they're easy and they're common everyday objects. But it's kind of crazy to remember that 200 years ago, bicycles didn't exist at all in any form. And then even after the original bicycle was invented, it took a couple hundred years, I think 100 years, for it to end up being the sort of bicycle that we see today that's safe and whatnot and to get around. So let me see if I can pull this up. We can do a live talk. All right, so this is, I guess, one of the first, let me pull it up on the left. This is one of the first bicycles from Wikipedia, and you can see that it's got the basic structure. It's got wheels and things like that, but it doesn't have pedals or a chain. And so you can sort of scoot around, but it's not a practical bicycle that we would see today. Here's the image of this fellow or I guess this woman running with the bicycle using their feet on the ground. Then there's another architecture which ended up coming up like this, where you have this massive back wheel. Again, no gears or no powering or anything like that. And it took a while before we finally got to the bicycle that we sort of recognize today, which is this sort of bicycle. It's the same thing for language models. A lot of the underpinnings were defined in Claude Shannon's paper, which we'll talk about in just a minute here. So it's not like these ideas are new or everything just came about again in one decade, but it took a lot of different innovations for this all to come together. So for a bicycle, you had to come up with a frame, so you could actually have something to sit on that wouldn't collapse. You have little things like grease and bearings that you don't think about were needed for efficiency. You could have the frame and the chain, but if you don't have any grease, your bicycle just gets stuck. It can't get anywhere. But then there's a lot of other factors, right? You have to have brakes and helmets for safety. If you don't have brakes or helmets, and you're always falling off your bicycle and dying, not a lot of people would be riding bicycles. We certainly wouldn't be letting children ride bicycles, right? It wouldn't be safe for folks to use. So a lot of time and research and investment goes into the safety of bicycles. And then there's also other factors like a global supply chain for delivering bicycles. It is very unlikely that all of you have a bicycle factory like right next to you. Maybe Chad does because he lives in a particular area which is famous for its bicycles. But I certainly don't have a bicycle factory near my life. But I still can buy a bicycle because it's been produced somewhere else and delivered to me. And this is the same with language models, right? Some language models aren't quote unquote produced on your computer. They're produced by other organizations, and they're shipped to you over the internet. And then lastly, for bicycles, we have sidewalks and bike lanes for usability. There was infrastructure built by the government and municipalities to make this all possible. This is all greater than just the mathematics and just transformers, but I bring up this context because we're going to talk about all of this again in our book club, because it's all these factors that have made these language models not just research interests and sort of small contained computational programs in, maybe like a Gmail or Microsoft Word or something like that, but suddenly now this useful tool that all of us have access to. All of this will end up becoming relevant again later on in this book club when we're trying to deploy our own language models on our own computer, because we're going to have to make, when you're doing it yourself, you're going to have to make all these decisions yourself. Just like if you were building a bicycle yourself, you would have to know about all of these things to make the right choices to get your own bicycle to work. And again, as a spoiler, we're going to get to a point in this study club over the next couple of months where we're going to be building small versions of these models ourselves and ideally deploying small versions of these models on our local computers. So the other analogy I want to give you to frame things is that if small language models are like bikes, then large language models really are just like massive semi-trucks. So with a bicycle, you can carry some cargo in a backpack, or maybe you have a cargo bicycle where you can strap a couple things on. And maybe you can move, like, let's say, a small load of groceries from the grocery store to your house. But to get to the grocery store, a semi-truck was used, and it moved those same groceries, right? So it's the same, maybe milk and eggs and things like that, but it's at a much, much bigger scale. So it's the same idea, right, that we want to move a unit of goods. We want to move milk and eggs. In your case, you want to move it from the grocery store to your house. But in the grocery store's case, it wants it moved from the farm or the supplier to the grocery store. Now, again, it's the same idea that we're moving something. And the bicycle is performing the same action as the semi-truck in that it's moving something. But because the semi-truck is so much bigger in its scale, it feels like it's a different thing. So in the use case sense, it's the same. But in the scale sense, it's completely different. And so you have the same ideas here in that you have grease and power systems and things like that for the semi-truck. But because it's so much bigger, it takes a different mindset to build those, and a different skill set to build those than it does to build a bicycle, even if the underpinnings are the same. I bring that all up to say that's what's happening with language models and what we're going to cover in the next couple sections real quick. It's that the small language intuition will give you the basic framework to think about these things, and then the large language model really is just scaling it to be just humongous and massive. But in that scaling, you end up with a bunch of different techniques and transformers and all this different TPUs and things like that to make that happen. I provided some additional intuition here. I won't read through all of it right now, and I do have to complete some of it. But this will give you another sort of analogy about how this all fits together. So the last one I want to leave you with is that, well, I'll leave it for later about transformers. So we'll talk about it in a second. Now, this particular section of the book is not completed yet. I still need to do tuning, evaluation, and actually add in a bunch of others, but that will be for the next book club. What we're going to go into next is small language model intuition. All right. Again, I've talked a whole bunch, So if you have questions, post them in the chat anytime. Kind of completed a large overview of a bunch of different topics, so let's narrow it down to one thing. So language models are useful because language is useful to humans. There's a lot of things we may want from a language model. So with causal inference, or like let's say linear regression, we're really asking only one thing of a model. We want the model to fit some pattern or help us understand one particular component of some study or some government policy or something like that. With language models, there's a bunch of different things we could want a language model to do. We want it to correct typos, like I have a couple in other parts of the section that we want fixed. We might want language models to correct grammatical errors. The subtle difference here is with a typo, we want the language model to understand that there is an issue with one particular word. With a grammatical error, it has to detect that there's an issue with a different sequence of words. These days, we may want language models to expand or summarize text. We might want them to reword text. We could want language models to translate text. We may want it to retrieve information. We might want it to answer questions and follow instructions, perform actions. And historically, different language models would largely be trained for each one of these. So, there'd be a typo correction model, a grammatical correction model for a Microsoft Word, let's say. But then if we went to Google, we would want Google to retrieve information by typing in a string, like find me a good place to have birthday parties. But now, as you folks know, with these newer class of large language models like Bard or ChatGPT, one language model can do it all, which is actually pretty insane. It's really interesting that instead of having models that are specific to one or two things, models are now being developed that can do all of these and do them pretty effectively. Even though these large language models can do all these big things, the fundamental intuition of these language models are all the same. They're all token predictors, or let's say for now, character or word predictors. Because I'm Bayesian, I like, this makes me happy. But essentially what they're doing is they're taking a bunch of strings. So these language models are ingesting a bunch of data, which are training examples. Like my name is Raveen, my name is Scott, and my dog's name is Spot. And it's learning the semantic representation of these words, let's say, through a couple different methods. But we'll start with this first method, which is just word prediction. So if you go to Claude Shannon's paper or some basic resources, you'll see syntax like this. The probability of a sequence of words is given by the previous sequence of words and the next word. So as a human, if I give you this sequence, the basics of, and you could say, is it the premise, the basic function, the basics idea? But with the grammatical error here, this would throw you off, right? This wouldn't be exactly what one of these things. All these words would work, but maybe they wouldn't work. And as a human, you can sort of reason it into it because you've seen a lot of English, likely, especially if you're in this particular stream. You've seen a lot of English, and you can intuit what's happened here. With a language model, the same thing is happening. You see a lot of strings, or it sees a lot of strings, and it figures out what the next string may be. So, for instance, if I want to predict what comes after name, in all these cases, is comes after name. So the probability of is 1. Oh, this did not work out well, but the probability of is 1, and the probability of name following my is 0, because in all of our cases here, name never follows, or my never follows name. If I were to tell you name my is Raveen, you would, as a human, understand that this is incorrect because you rarely ever hear this string or see this string. In a basic language model, the same thing happens. It sees a bunch of strings and it ends up constructing a bunch of basic probabilities. Now at the bottom, I provided the two references that explain this well. One is this the mathematical theory of communication. This is Claude Shannon's paper from 1948. In here, I'll provide a direct link. It's not too long of a paper. It's about 50 pages, but in here he provides that exact same understanding. It's a little more mathy. He uses letters, but you can see these probability tables here that he constructs. Again, this paper is from 1948. It's actually really fascinating how Claude Shannon was able to come up with these concepts more than, in this case, 70 years ago. So you have that same idea here. We can calculate, if we have an arbitrary language, we can calculate relationships and between words or characters through basic probability tables. Now, Claude Shannon in this paper then extends it to Markov chains. So he's a super smart guy. He first defines the fundamental definition of entropy, which underlies basically almost every machine learning algorithm that exists right now. It's actually this particular calculation right here. But he goes on and he defines language models, basic language models with noise, and then I just passed by it, but with Markov chains and probabilities as well. Let me see if I can find that. Oh, this is the appendix. So over here with Markov chains. If you really want to understand the fundamentals, very well worthwhile reading this paper and going through the details. But otherwise, there's a really nice YouTube video here that explains it in 4 minutes extremely well. We won't watch the YouTube video here ourselves, but I suggest watching this over coffee to get a better understanding. The basic understanding that I want you to be left with here is that all language models, including ChatGPT and Bard and all the fancy new ones, they do a version of this, right? They take in a bunch of text, in this case, internet scale text, and they learn these patterns through particular manners, trying to estimate these probabilities and coming up with these probabilities. Once we have these probabilities, then there's a lot of different things we can do. We could create a grammatical check. So if I give you the string name my is Ravine, and we give it to this probabilistic model, in this case, because the model has never seen name my in that particular order, it can flag that this is a very unlikely, or in this case 0% likely, combination of words. This must be a typo of some sense, because there's no way that this could happen. Another thing you could do is generate text. So if you fed it my, because it has a probability tree and it's seen different sequences, it can create different strings that are original and that you've never seen before. In this case, it might create the string my name is Spot, for instance, or my name or my dog's name is Ravine. Later on, I might end up creating a Python version to show you how this works in practice. But for now, these are the two fundamental intuitions about large language models or language models in general. It's that they're given a sequence of text. They learn the probabilistic representation between different pieces of characters or words, or later on, which we'll talk about, tokens. And then once you have this probabilistic representation, you can reapply these probabilities in a number of different ways. You can use it to check the correctness, let's say, of a particular sequence of strings, or you can use it for grammatical checks, or you can use it for any of the purposes that we have listed above. Although this feels simplistic, this really is, again, the fundamental underpinnings of all language models. So just like we use the bicycle analogy and the semi-truck analogy, the fundamental underpinning of a bicycle and a semi-truck is that you have a structure, whether that be the bicycle frame or the semi-truck's structure and frame itself. You have wheels, you have tires, you have a power source, whether that be a human or you have the engine of the truck. And then with all of that and some steering, you can move around goods. With a bicycle, you can move around, a couple milk and eggs. And with a semi-truck, you can move around an entire load of cargo for an entire city or an entire town or village or an entire grocery store. The fundamental ideas are the same between both. So seeing no questions, or maybe I should always double check. Seeing no questions, I'm going to move on to large language models and transformers. Now, again, I'm not going to go into the details of transformers. There are tons of great blog posts and videos about transformers and the various parts. I'm going to talk through it at a high level, and then I'm going to come back to these resources and explain why I believe these ones are the nicest ones if you're intending to learn transformers all the way through. So one thing I can say about transformers, the highest level, and the one that you probably already know, is transformers are the newest neural network architecture that is able to that is the underpinning of these new round of language models. Transformers are particularly good at this because transformers have a couple of great computational and mathematical tricks that make them scale really well. Scale better than recurrent neural networks, which or in LSTMs, which is the previous approach. You've also probably heard that these methods are called attention. So let's talk through the main ideas of a transformer and really get into it. I'm going to refer to one of the articles here, and then we'll come back. So this GIF I found to be really nice because after watching it a couple times, it both communicates the complexity of transformers, but also then summarizes it well. I was debating taking this GIF and pulling out each frame because this particular author did a really good job. But you can see him, and I'll let this play on loop while I'm talking. So in a transformer, there's sort of multiple different levels, and one challenge I had when I was learning transformers is people would be talking about different portions of these of the transformer abstraction, but you really need the full stack for all of it to work. So first, I wish I could pause this. Maybe I can, maybe I can't. Okay, I can't, but I should. Well, this is gonna be fun because I don't have to time my speaking with it. So you have a couple of different levels. You have the thing called attention, which is what you see right here. Then you have the thing which is called encoder, but all of them are really just the same multiplications and weights that we've seen 1,000 times. So in a transformer, let's see if I can show it here. Just like our first book club, at the basic level, there's nothing really new. You have a set of weights and a bunch of matrices, and you multiply them together, and you get some values. That's the same for recurrent neural networks. That's the same for convolutional neural networks that we talked about the last time. That's the same for neural networks from the 1950s. Like this basic matrix multiplication with weights is all quite the same. What changes though with transformers, and which makes them quite interesting and work well, is this concept called attention, and this is the name of the paper. Attention is all you need, which is where the transformer came from. So it's the first clue that this new thing, attention, is the difference in what makes transformers particularly cool and work well. When you have neural networks like let's say convolutional neural networks, the sort of defining characteristic of that is what's in the name. It's the convolution, which takes a bunch of pixels and sums them together, as we have seen in this picture. So this is the idea of a convolution, and this is sort of the defining characteristic that makes a convolutional neural network a convolutional neural network. In a transformer, that same concept, or one of that same concept, is attention. And what attention has is it itself is composed of three particular ideas, which is the query, the key, and the value. So I'm going to attempt to give you an intuitive explanation of query, key, and value before we bring it back up to attention. If I give you the string, I went to the grocery store and the hardware store, walked around, bought nails and bread, which did I buy where? As a human, we learn to pay attention to certain words. We know that to answer the question, which did I buy where, we don't need these words. We don't care about and. We know to ignore walked around, and we know the relation semantically is between grocery store, bread, and hardware store and nails, and they're out of sequence. What a transformer does, and what attention does, is it's the mathematical representation that helps learn the semantic relationship between nails and grocery store and hardware and bread. And if I pull up the paper, because it has a really good picture of that. The classic example that's from the paper is a machine translation example, and it is this picture here. I will let you read the paper itself, but what this is the sort of this was the first visualization in the original paper that shows the relationship between different words. Let me see if I can rotate this for you. I might not be able to. Okay, you might have to rotate this on your own. But what it is it took a bunch of words, let's say a string of words. It is in this spirit that the majority of American governments have passed new laws since 2009, making the registration of voting process more difficult. And what the attention mechanism does is learn that that the word making is related to the word making itself, and not so much to this first string. It's related to more and difficult and making, and these are the words that show up more in context with the other ones. The reason this attention mechanism is so powerful is that when we go to our original definition in our small language models, while this theoretically could scale to an infinite amount of parameters, in practice it just doesn't. And I talk a little bit about n-grams, and Claude Shannon talks about it a lot later. But trying to represent all languages in this probabilistic manner doesn't scale very well. It turns out that attention, which uses these set of matrices, does scale really well. And once you have matrices that are large enough, you end up being able to semantically understand the relationships of words in this particular way that creates ChatGPT and all these sorts of different models that we can get now. In attention, when you read about it, there's three particular words that come up, three particular concepts that subcompose attention. It's the query, the key, and the value. And these are actually matrices themselves. So the query, the key, and the value are matrices, just like the matrices of values that we've had in our previous book clubs. So in the rough analogy that I found the best is from Lee Verma's blog post, which I will show you here, where he also goes through the attention mechanism. Here you can see that he writes about queries, keys, and values. They're nothing more than weight matrices. And he provides a really good, I think, intuition about what these are. So let's say you log into Medium, which is the blog posting site here. You look for some topic of interest, which is transformers. That's the query. Our query is an article. I want an article about transformers. Medium itself has two things. It has the title of the article and it has the hash of the article itself. In this case, that's the key and the value. So the key would be, in this case, a query, key, and value and attention mechanism. So this particular title doesn't contain transformers, but it does contain query, key, and value. The hash is the article itself and the text in the article. Now, there's going to be some similarity between the query I have, which is I want to learn about transformers, and titles in a database. Because transformers and the word query, key, and value now appear a lot by each other, there's some semantic representation and similarity between the word transformer and those particular terms. That composes the dot product, which combines these three matrices together. Once you take that dot product, you take out the hash key that has that maximum value. That hash key is the article, and then you return that value, saying that this hash key has the biggest value, and that's the thing I should pay attention to the most. If I go back to the original paper, you see that here they encode that with the strength of the lines, and they also encode that with the matrice represented here in the different colors. So to fully understand transformers, these are the three concepts you think you should really dive into, is to understand that at the fundamental level, there's nothing more than matrices that are just a vector of numbers that get multiplied together. The attention mechanism is composed of 3 of these matrices: the queries, keys, and the values. And if you just multiply them together with a dot product in a right particular way, and then scale them up, you get attention. And then with attention and a couple other tricks we'll talk about, you end up getting to transformers. So bottom level matrices, middle level, next level up, query, keys, and values. Level up above that is attention. What I'll show you here, which I think is a really good way to take this from an abstract idea to code, is if you go to Flax, which is our favorite library, and you just look at the code implementation of self-attention. So this is the attention module in Flax. It's great because it's not that long. It's actually very well written. And I've highlighted for you here the single line in this entire thing that is those attention multiplications that we talked about. Well, there's actually 2, but the most important one is right here. It literally is, again, it's just the query and the key, and you multiply them together right here, and you get the attention weights. And then if you go down some more, which is it's in right here, you take the attention weights and the value, and then you end up getting the final matrix product result. So here's the value. Here's the query, and here's the key. So for those of you that like to learn with code, this I again find to be the best implemented in a library version of query, key, and attention. And I will also link another resource where somebody's created this themselves in NumPy. But these the code commenting and the production grade value of this makes it, to me, the best code reference that I have found. All right. With that, even though you have attention, that isn't all that's needed in a transformer. And that's not all that defines a transformer. It is certainly the most important component, as the authors of the original transformer paper call it themselves, because the paper is titled attention is all you need. Like that is what they're highlighting. But there's a couple of other mathematical tricks that they use, which is self-attention. Well, I'll talk about self-attention positional encoding, but I actually want to skip to softmax first. So another thing they do is they use softmax. Now, softmax isn't just a neural network concept. You see it in Bayesian libraries all the time. We use softmax in PyMC all over the place. When you see the definition of softmax, it can look a little intimidating. You've got a lot of different terms, but it's not too bad implemented in code. The general idea behind softmax is if you end up with any arbitrary vector of any arbitrary length, let's say in this case I have 0.3, 1.2, 1.8, or 0.8, you just, let's say, run this one line of code which exponentiates each term and then divides them by the sum of the exponentiation. And what you get out is you get out a proper probability vector. So even though this value doesn't add up to 1, once you apply a softmax to it, you end up seeing that, okay, this thing has let's say 0.48 probability, this is 0.32, and this is 0.19. And if I can do my math correctly, this should all sum up exactly to 1. So one use case of softmax is taking any arbitrary length vector and turning it into a proper probability vector that you can sample from. We'll see that in the transformer architecture in just a moment, but it actually has one other thing that it does in the transformer itself. It's the normalization layer, it both normalizes, wow, I'm really running out of words today. It's the activation function and the normalization at each layer weight. So on our previous neural networks, as we covered in some of our previous book clubs, you had to add, ReLU or these other things to take a neural network output. Let's see if I can show that to you. This one does not. It does right here. Okay. So in neural networks, you have this activation function. Let's say this one's linear. And when you change the activation function, this actually has a lot of effect on what happens in the final neural network result. So let's say I change my linear activation function to sigmoid. Well, this is not able to fit this data very well. But if I fit it to things like ReLU, suddenly the behavior of this neural network changes pretty tremendously. By doing nothing in the data or the architecture of the neural network itself, I go from not being able to fit the data at all, like this is a terrible fit, to being able to fit it quite well. So in addition to the architecture of the neural network, the weights and the attention or whatever else it might be, a lot of research and time is placed on the activation function. And in transformers, they make another key change or key idea is to replace the activation functions with softmax. So if I can go to my go to our blog post here, we might be able to see it for just a moment. Did this stop showing me my GIF? I lost it. Well, oh. Let me give you a chance to show it to you real quick. All right, so we might see softmax here in just a second. There we go, softmax, and then that slams into attention. So that softmax is another key change that you can miss, but it's another factor that made these things work particularly well. This particular transformation, and it occurs at a couple of points. So now we've covered query key and value, which are the basics, attention, which composes into self-attention and positional encoding, which we'll cover in the next book club. With that, we also include softmax. And if you take all those and you plug them in together, you get this. And this is the diagram from the original paper. You'll see it all over the place, but this is the highest level of a transformer. So in here are the query keys and values. In here is attention, as you can actually tell, because it says multi-head attention. In this attention, there's a softmax transform. And then what the authors of this paper did was they then took attention and they stacked a bunch of attention layers together. So now this one block is composed of all the things that we talked about above. So now they took this attention block and they put it into a particular architecture. So on this side they have one thing, and on the other side they have another thing. It's not labeled here, so I'm going to replace this with a label copy. But there's this last thing when you're reading about transformers is this encoder and decoder stack. So in the original Attention Is All You Need paper, they created a model, and this was the encoder stack on the left, and then this is what's called the decoder stack on the right. If you read about transformers a whole bunch, you're going to hear about these encoder models, decoder models, and encoder-decoder models. To be upfront, I have a little bit of a loose grasp on the practicalities of these, aside from the mathematical specifics, but I want to point you to this particular website, which, in my opinion, does the best job of explaining this. Oh man, here we go. So this particular website, published by Soren D, provides a pretty good explanation. So I'll read through it. I'm going to have a tough time answering specific questions, but essentially, here's the encoder-decoder on the right, the left being the encoder, the right being the decoder. And what ends up happening in the original paper is that the encoder stack takes in a string of text in English. The decoder model takes in a set of text from French. And then what this thing is able to do is then translate the text from English to French. And so encoder-decoder models were able to do these things: translation, text summary, question and answering. These are actual implementations of the encoder and decoder models. So there's papers for you to refer to and actual models that have been constructed in these particular architectures for you to go read more into. On the other hand, you may have encoder-only models, which just take the left. And my understanding of encoder-only models is they feed in a set of strings and they just give you a set of latent probabilities. They encode the text into probabilities. Or sorry, I shouldn't say probabilities, but I should say an embedded or matrix representation. And once you have this, you can do things like classify text. Like you can take news articles and my book and maybe another statistics book and be able to say this is a statistics book, this is a news article, this is a child's essay, because you don't need to be able to decode the text back into actual text to understand what's going on. You just need to get a representation and measure the distance between representations. And then the one that is probably the most interesting to folks right now is the decoder-only architecture. The reason is the decoder architecture is what powers these chatbots that we talk about the most. So, GPT 1, 2, 3, and 4 are decoder-only architectures. Google's Lambda, also Bard, are decoder-only architectures. And so decoder-only architectures are the ones that we probably are the most enthralled by, because they're the ones that make these cool chatbots that we like talking about. All right. So when reading about transformers and going through transformers, the reason I bring up all this in the guidebook is that some articles go all the way down to the basic with the matrices, and they talk a lot about a query, key, and value, and attention as one component. Other articles do a better job mentioning that there's other parts of transformers that aren't just attention. There's things like softmax and more components that make up the transformer itself. And then other articles focus on the decoder and encoder stacks, because there are transformers that are decoder only, encoder decoder, or encoder only. And when I was trying to learn this stuff again, I was getting stuck because sometimes I would see half of this but not the other half. I was reading about ChatGPT. I would not see the encoder stack but only the decoder stack, and it made the concept of a transformer slippery. So again, this being a guidebook, I hope I provided you everything that you've needed here to fully learn the transformer. Me explaining it to you in this 40 minutes is probably not going to be sufficient, so I encourage you to go into all these various resources and read into which parts you're particularly interested in, whether it be the code or the intuition. And there's a couple of other articles I'm going to add into here as well, which I also think do a pretty good job explaining this all end to end. So with that, those are the 3 sections of the guidebook that I wanted to cover. Surprisingly few questions today. I always never know whether questions mean that I'm doing a great job or that you guys are all lost. But I'm hoping that this was at least useful in the sense that now you have an overview of the landscape. So it's not so much that we've explored every single part of this landscape of transformers, but I hope again with this guidebook you can see the big structural pieces and have references to go into each one of them. It's really the combination of all of these things that is what's making the generative text and the natural language processing area such a hot topic right now, right? You've had these concepts again for many years. You've had this single building from Claude Shannon that's been there since 1948, and for a long time people were struggling with making it scale. I mean, the ideas are all good. The ideas were still the underpinnings of everything that we do today, but we couldn't scale them really well. And then we end up with neural networks, which we talked about, that are coming out, in the 60s, 70s, and then the 90s, and even the early, 2010s. And people tried scaling them to do natural language processing. They were blowing out benchmarks for image processing in 2010, with ImageNet and these sorts of things. But they weren't doing so good, as good as they could with text. And then suddenly in 2016, I think, let me just double check. 2017, you have this paper, Attention is All You Need. 2017 doesn't feel that like long ago, but it also was more than half a decade ago. So suddenly these folks published a paper, and now this new architecture is just blowing out all these natural language stuff. It's just creating all this cool technology such as ChatGPT. And the reason it's able to do this is because it just does a really, really smart and computationally efficient matrix multiplication. Like, it literally, let me go up to this line. Literally the genius of these guys to realize that if you just get 3 matrices and you multiply them together, which computers are fantastic about, you can do that at scale. And then if you just apply a softmax transform and do a couple rearrangements of components that we've already have really good computational abilities to do, which is if you just take a couple matrix multiplications, you softmax them, you do some addition and normalization, and you do it a couple of times, you've got the underpinnings for what is the coolest technology and the fastest adopted product of all human history, which was ChatGPT. It's so wild to me that you can go from just a basic intuition like this, which seems really easy, to then like, well, why don't we just set up matrices in a particular fashion, and then let's just scale it to be humongous, and now we've got the semi-truck. We've gone from the original bicycle to now the semi-truck of moving language and understanding language and things like that. What we're going to cover in the next sections of the book club, before I get to questions here in a second, is we're actually going to implement a transformer from scratch. We're going to basically follow Andre Carpenthy's transformer Shakespeare model. Let me pull it up just so you folks have that right now. I'm gonna cover this in a summarized version, but this is the I think, well, definitely. Oh, sometimes I'll put it in the YouTube chat. This is the best single resource I found from a literal expert, like one of the world's leading expert, coming down and explaining this in code with a data set that'll fit on your computer. Explaining how this whole thing works end to end. So this will be the primary reference for our next book club section. We'll cover elements and screenshots from here, and then I'll also show you the implementation of this that I built in Flax. Let me see if I can pull it up. I think I called it Jax GPT. See if we get lucky. Let's grab it here in a second. I have so many resources that I have too many repos now at this point. I will find it later and show it to you folks, but it'll be a combination of the video that I posted to you, and then and I shared there, and then also some additional commentary I have, so you folks can understand that. But the idea being is we're going to do this actually in code, so this won't just be me wildly gesturing with my hands, but we'll get back to a Jupyter notebook and code examples and talk through this all end to end. But I just want to say to you again is that if you go through this and you read these and get an understanding of both this and I think and Claude Shannon's paper, you will have a really good understanding of transformers and how they work in language models. And it won't even just be transformers, but just language models in general. And in my opinion, you'll have an understanding that's better than 99.5% of ChatGPT or Bard users, because all that's happening, frankly, like all that's happening at the very core of GPT and Bard is this: a bunch of text is fed in to learn a bunch of matrices, which we call weights or checkpoints. Those are saved, and then once you load those into memory, and give somebody access to it like this. I guess I don't have this here. So, okay, I guess I'm not using. Well, let's see. Let's see if it does it without logging. All right. Hello. Where can I find a bike in Portland? Like, all that is happening in this is that this string is being fed into a decoder-only model, which understands the semantic representations between bike, Portland, and all the text on the internet, and it's able to then produce this answer to you. It's like quite crazy to me how such simple ideas can create something that's so powerful. With that, let me go through the questions. We are almost at the hour. Rahul asks, in the transformer architecture, the decoder stack takes input from the encoder stack. Does that mean having a decoder only model GPT, there must be an encoder side? So Rahul, my understanding is, and I don't want you to take this as fact. This is where I want to say I have a loose. Oh, actually, this is something that confused me. We'll talk about this more in the next web session. Is that the word encoding is overloaded in the context of transformers, and it took me like forever to understand this. But essentially, even though this is called an encoder, what is also happening is that the text that's being fed in is also being encoded, but it's two different. I don't know why they did this, and it's actually kind of frustrating. This is an encoder, and the text is also encoding, and what the word encoder means at the architectural level is different than what the word encoding means at the text level. I'm going to give you a little bit of a preview here with sentence piece. What happens with the text, and this is why I was careful not to say words or characters and things like that, but what happens with modern transformers is you don't feed in just words. Like the neural network isn't learning words, and it isn't learning characters. It's actually learning tokens, which is why you hear the word tokens all the time, like 2,000 token context window or 1,000 token context window or whatever. So what happens is that you have a raw sentence, and it gets translated into an intermediate representation. Okay, the library is sentence piece, and so this is Google's open source tokenizer. And you can see it also uses the words encode all over the place. But the encoding of text is different than the encoder of a transformer. So it is so incredibly confusing. I don't know why they did this, but a decoder only transformer model is only this right part. It is not this left part, which is the encoder, but transformers in natural language models of all type encode sentences and encode input strings, I should say, into an intermediate representation. And the encoding of a string is a different action than the word encoder in a transformer, which refers to the left side of the transformer block. It's part of the reason I was confused for months why they did this. This will make much more sense next session, where we actually go through this in all fully encode, and you can see the encoding of text being different than the model architecture itself. All right, Chad says that was great overview, helpful resources. Thanks. Well, I'm glad you guys are enjoying this as always. I feel like with this book club, I'm sort of winging it each time, going from one topic to another. But I'm glad that this is helping. If there's any other questions, please go ahead and drop them in the chat now, because we're reaching the end of this particular session. But let me tell you what I plan to do the next couple of weeks, so you folks have a better understanding. What I'm going to do is I'm going to write out the section on transformer training. It's going to largely reference the video that I posted in the chat. So what you can do if you want to get ahead is go through Anja Karpathy's video that I put in the chat. That is going to be by and large the majority of next week's session. That being said, what's done there is a basic version of transformer. There are then additional steps that happen afterwards in the model pipeline. So even after a basic model is trained, or what the word is called pre-training, to produce something like a ChatGPT or the useful models that you see, there's various versions of tuning that happen. There's what's called supervised fine-tuning. There's reinforcement learning with human feedback. So it's not just that you take a transformer and train it, but it's also that you do a bunch of different additional steps to get to that training. So next week, what the theme is going to be, it's going to be all about like I'm going to kind of working title, but transformer training in practice. The core of it is going to be the video that I've linked, which is where Anja Karpathy covers the basics. And then, actually, interestingly enough, because Anja Karpathy is a guy that does everything, that's his basic lecture. He then gave a talk at Microsoft about a month ago, where he then covers the extreme end of it, where the production grade end of it, which is supervised fine-tuning, reinforcement learning with human feedback, and things like that. So we probably also will cover, use him as a reference for the other side of it, because Anja Karpathy both builds bikes in his home on Colab, which is the example that you have in the video I linked, and he also builds the world's biggest massive cargo freighters of GPT and everything like that. So this guy has resources on both. We're going to cover both sides of it. We're going to build a bicycle ourselves, if I use the analogy, because we can build bicycles in our home. But none of us can build massive cargo freighters in our home. Like I don't think anybody here has a house where they could build a semi truck or an ocean freighter. But we want to talk about the connection between both sides of it as well. What that means practically is that I will be writing out those two sections over the next couple of weeks. I'm hoping to get those published. I guess I have a little bit in the US. We have July 4th, so I'm hoping to get these published a little bit after July 4th. Let's say July 6th or 7th, so you guys have a little bit of lead time to read, and then we'll hold a session after that, either the Sunday after July 4th or the Sunday afterward. But by now, you guys know how to get a hold of me. We have our fantastic community forum, which I will post on, but also our email list. The last ask I have of you before we leave is, as you can tell, I'm writing this guidebook as we go. So if you're reading this and there's anything else you would like me to write about, or some references you find, or any modification you would like to make, please just go ahead and you can email me directly, you can ping me, or you can just go to the repository and open an issue. I guess I'm not logging to get up here, but you can go in and just open an issue on this and tell me you want something changed. Because in this interesting book club, which is now turning into a book writing club, I'm building this for you folks, and if there's anything I can do to make it more useful for you, let me know, and I'm happy to incorporate it. So with that, I hope you now have references to everything you need to learn about the basics of language models and transformers. I'll publish a couple more articles in there so you can watch them and peruse them yourself on your own time, and then I'll build out the transformer training, supervised fine-tuning, and shaping sections for next time. So enjoy your Sundays wherever you are. Thank you again for spending a little bit more than an hour with me, and I will see you in the next session. Bye, folks.